Hello students, in this video we'll discuss the Gauss Divergence Theorem. The Gauss Divergence Theorem states the following. It says given a vector field V of x, y, and z, and a closed, this is important, so this is a key feature of the Gauss divergence theorem. You need to have a closed surface, so you want to think of like a box or a square. You want to think of like a box or a sphere or an ellipsoid. A closed surface, S, with outward pointing normal n hat. Then, if we look at the surface integral over the closed surface, our circle one's closed, of the vector field V dot n hat d sigma, where that's your surface area measure, is equal to the triple integral over the interior of the surface of the divergence of the vector field with respect to the volume measure. So let's see an example of how we can use this Gauss divergence theorem. So here's an example. So let S be the unit sphere. X squared plus y squared plus z squared is equal to 1. And V of x, y, z is the vector field x plus y, z, y minus x, z, and then z plus x squared plus y squared. So there's our vector field. And let's find this flux. Find the flux of V dot n hat d sigma, which is of course the flux, we call this linguistically, is the flux of V over the surface S. So we're computing this flux integral. What we'll immediately do is we'll just immediately apply the Gauss divergence theorem. So by the Gauss divergence theorem, Gauss divergence, this will be the triple integral over the interior of the unit sphere. So x squared plus y squared plus z squared less than or equal to 1. That's the interior of the sphere. And then we compute the divergence of this vector field. So let's compute the divergence of V. So what's the divergence of V? Well, it's going to be the x derivative of the first entry, x plus yz, plus the y derivative of the second entry, plus the z derivative of the third entry. And we can see by a quick calculation that there's no x derivative of these terms, there's no y derivative of these terms, and there's no z derivative of these terms. So we get an x derivative of x, which is 1, a y derivative of y, which is 1, and a z derivative of z, which is 1. So the divergence of this vector field is just equal to 3. So I have 3 times dv. And so I don't even need to do a triple integral because it's an ordinary volume. And so this is just going to be 3 times the volume of the interior of the sphere. And so what this will be is it's going to be 3 times 4/3 pi r cubed. That's the formula for the volume of a sphere of radius r. But of course here we're on the unit sphere, so r is equal to 1. R equals 1. And so we're just going to have a 4 times pi. And that is our flux of this vector field over the surface. Now, one thing is important is that we're looking at the outward pointing normal vector. If we invert the orientation and have the inward pointing normal vector, then we'll get a negative sign difference. So oftentimes you're going to see problems where you might not get the answer in the back of the book, or you might get a different answer because your normal vector is pointing in the opposite direction. So be careful if there's a negative sign discrepancy between your answer and answer you're referencing. Thank you very much.